All right, here we have lesson 20.4, the fundamental theorem of convergence. So today we have three theorems to start us off. So theorem number 1 says if S sub n never increases as n increases, but never becomes larger than some finite number b, then as n goes to infinity, we say that S sub n approaches S. Remember that notation for S, this is here our infinite series notation. So as n is going to infinity for S sub n, then that's going to approach the infinite series value where S is less than or equal to that finite number b value that is in the hypothesis of this theorem. So this is something that we've been talking about for a while, but we just never really formalized it in this way. All right, Theorem 2 and Theorem 3 are very, very important theorems, and these theorems are often misunderstood. So Theorem 2 says if a series is convergent, so we must know that the series is convergent in order to use this theorem. Then it says that the nth term, now the nth term we know is notated in this text as u sub n. Then the nth term must approach a limit of 0. So mathematically writing that out, we have, if we know that the series is convergent, then the limit as n approaches infinity of u sub n will equal 0. Again, I want to specify that we must know that this series is convergent to begin with. So we already know whether it converges or diverges, and we've decided that it converges. And since we know that it converges, we will automatically know that the limit of u sub n will equal 0. Okay, we'll come back to this theorem in a little bit and talk more about it and talk more about kind of where you might be confused with this theorem. Now Theorem 3. Theorem 3 might look a little bit similar to Theorem 2 because here we're talking about a limit as n goes to infinity of u sub n, and it has something to do with 0 on the right hand side. Same thing here. We have a limit as n goes to infinity of u sub n has something to do with 0. The difference is this equals 0, this does not equal 0. Also difference is this is the hypothesis where this is the conclusion. All right, so Theorem 3. If the nth term of a series does not approach a limit of 0, then the series is divergent. So in this case, this is a way to tell that a series is divergent. Whereas in Theorem 2, we already knew the series was convergent. So Theorem 3 says, if we have the limit as n approaches infinity does not equal 0, so if this is true, then we can conclude about the divergence of the series. Okay? This only proves divergence. And I want to specify that, because sometimes students will want to use this theorem incorrectly and say, well, okay, well, if the limit does equal 0, then it converges. It does the opposite. So they want to say that if the opposite of this is true, then the opposite of this is true. Okay, well, we'll look at that in a little bit. Okay? All right. So Theorem 2 and Theorem 3, very, very, very important theorems. So let's talk a little bit more about Theorem 2 and Theorem 3 and relate that to some things that we know in geometry. So remembering our conditional statements from geometry. So we have 4 conditional statements in geometry. Okay? And then we're going to look at what's the relationship between these conditional statements. And then we're going to relate those to Theorem 2 and Theorem 3. Okay? All right. So let's first list the 4 different conditional statements that we have from geometry. So the 4 different statements are the conditional. We'll start with that. Then we have the converse. Then we have the inverse. And last, we have the contrapositive. Okay? And the notation that we're used to seeing with these conditionals is if P, then Q. Whoops. So let's go to if P, then Q. So if our conditional starts off as if P, then Q, we want to fill in the other 3. So if you want to go ahead and see if you remember, pause the video right now and see if you can fill in the other 3 conditionals. All right, we're back. So the converse, what you should have done is the converse was if Q, then P. And so we want to relate each of these back to the conditional. So the conditional is our main condition, or our main statement, our first statement. And then the converse takes that conditional and it switches. It switches the hypothesis and the conclusion. Then we have the inverse. The inverse then negates the hypothesis and the conclusion. And when I say negates the hypothesis and conclusion, I'm referring to the conditional. So you can see here that the conditional is if P then Q. And if I say, okay, if P then Q, then I just put if not P, then not Q. So the inverse negates the conditional. And last is the contrapositive. The contrapositive is not Q, then not P. And if we think about what this means in relation to the conditional, think about what would it do? How would you describe it? Does it switch? Does it negate? What's the relationship between the contrapositive and the conditional? All right, and hopefully what you thought about was that the relationship is that it switches and it negates. So it does both. So we can say that this one here switches and negates. All right. And so now here we are ready to continue on and talk about the relationship between these four. Okay, so using these four, we want to talk about then the converse of Theorem 2. So looking at the converse and looking at Theorem 2, let's go ahead and write the converse of Theorem 2. So a converse we know is going to switch. Here we have Theorem 2. So if we just go ahead and we switch the hypothesis and the conclusion of Theorem 2, what are we going to end up with? So we're going to end up with if, and now we start off with the original conclusion. So if the limit as n approaches infinity of u sub n is equal to 0, then the old hypothesis becomes now the conclusion. So then the series converges. All right, so looking at that converse of Theorem 2, we want to investigate now the truth value of that converse. So is this converse going to be true, or is this converse going to be false? And how do we know when a converse will be true, when a converse will be false? Is there a relationship between the truth value of the converse and the truth value of the original theorem? Okay, so looking at Theorem 2, let me give you two series in which we know whether they converge or diverge. Or I know whether they converge or diverge, and I'm going to tell you what they do. You guys don't know how to prove it yet, but you will in the future. Okay, so here we have series A and we have series B. So series A right here, here's the series, and I'm telling you that this series diverges. Series B, here's the series, and I'm telling you that this series converges. Okay, now the hypothesis of this converse of Theorem 2, the hypothesis is if the limit of u sub n is equal to 0, then we can make this conclusion of convergent. So we need to find the limit of u sub n. Okay, so for each of these two series right here, series A and series B, go ahead and find the limit of u sub n. So for series A, find the limit of u sub n, and for series B, find the limit of u sub n. So we have limit as n approaches infinity of u sub n, which in this case is 1 over n. On the right, we're going to find the limit as n approaches infinity of u sub n, which in this case is 1 over n squared. And we're going to calculate what each of those limits is equal to. So you have that each of them is equal to 0. Okay, so that's the hypothesis of this theorem. So if the limit of u sub n equals 0, yes, that's true. Yes, that's true for both series, series A and series B. Then the converse of Theorem 2 says that would mean that the series converges. Is that true for both series? No. So the first series diverges, the second one converges. So series B, it works, But series A is a contradiction because it says diverges. So this contradicts here. So if you have one time where it contradicts, what do you have to say about the truth value of that theorem? Or of the converse of the theorem? It's not true. So that means that this here, because of that contradiction, put a little therefore, this is false. This is so very important. Because what I see happen very often is students are trying to use Theorem 3. Theorem 3 says if the limit of u sub n doesn't equal 0, it diverges. And then what they want to say, but then the opposite's true. If it does equal 0, it must do the opposite of this. It must converge. No, that's not true. Okay? So do not use that theorem incorrectly. Make sure that this theorem is only being used when the limit does not equal 0 to make the conclusion of divergent. This theorem does not tell you anything about convergent. Okay? So then here at the bottom, you see which conditionals are logically equivalent. So this is another term from geometry, logically equivalent. Thinking about, well, what does that even mean? Logically equivalent means that they have the same truth value. So if one of the conditionals is true, no matter what, the other conditional is going to be true. If one conditional is false, no matter what, the other conditional is false. So there are two pairs of conditionals, of these four conditionals, for which they are logically equivalent. So one pair, first one, conditional and contrapositive. So this means that anytime the conditional is true, the contrapositive will always automatically be true as well. So you could switch and negate any theorem and it's still true. Always, 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 always. Well, if that's the first pair, that only leaves two for the other pair. So the second pair that go together then are the inverse and the converse. So if you know that the inverse is true, the converse is automatically true. If you know that the converse is true, the inverse is automatically true. All right? So the truth value is always the same. So if conditional is false, contrapositive is false. If contrapositive is false, conditional is false. If contrapositive is false, what do you know about the inverse? Nothing. You can't relate them if they're not logically equivalent. So the converse tells you nothing about the conditional. The converse tells you nothing about the contrapositive. The inverse tells you nothing about the conditional. The inverse tells you nothing about the contrapositive. Okay? All right. All right. Theorems 4, 5, and 6 here are more or less properties, kind of algebraic type of properties that go with these series converging or diverging. Okay? So in theorem number 4 says that if you're given any convergent series and a finite number of terms are changed, deleted, or added, and this has to be a finite number. You cannot have an infinite number of terms being added, changed, deleted. It has to be a finite number. So there's 5 terms that are added. There's 1 term that's subtracted. Okay? Finite number that's changed, deleted, or added to the original series. Then the new series also converges. So put that in a different color. If you know that the series converges and you add, change, delete a finite number, then the new series will also do the same converging. Okay? It doesn't necessarily go to the same value, but it will also converge. Okay? Sometimes it goes to the same value, sometimes it might not. Note, if this original series diverges, then the new series also diverges. So same thing works. If you know that a series that has a finite number of terms being changed, deleted, added, that diverges, then your new series will diverge. Okay? Theorem 5 just says that if you take a series that you know what it does, and you multiply it by a constant, so C here is the constant. So if we take this series, we multiply it by a constant, it's going to do the same thing. So given this series with C, U1, C2, U2, U3, and so on, C is a non-zero constant, because if it's 0, it's just everything is 0. If you know that that converges or diverges, or that will converge or diverge according to the series without the C in it. So kind of like you're factoring out the C, and then you're working with the series, and then you're saying, oh, well, it's going to do the same thing if I multiply the C back in. Okay? Theorem 6 says, if you have a series that's the sum or difference of two series, so V and W, okay? And if you know that those two series converge, those two series both converge. This is not true for divergence. If you know that both of those series converge, then the sum or difference will also converge. And the limit of that series will equal the sum of the two limits. Okay, this is for convergence. If you have series that diverge, it gets a little sticky with when you can say things are going to happen the same way. If you have a convergent plus a divergent or a divergent minus a divergent, it gets a little tricky. Okay? So this is for two converging series. All right, so those are properties, theorems that are kind of more or less algebraic type of properties that go with our convergence or divergence. And then let's take a look at some examples. All right, example number 1. The directions for all these problems are going to be determine whether the series converges or diverges, and of course support our answer. In this chapter 20, every answer will be written with a sentence for your final statement. That final sentence will include all the information that supports your answer and that demonstrates the interpretation of the mathematical algebraic work that you do. Okay? So just know that every single one of these answers is going to be followed up with a sentence. So here, we're given this series, 1 minus a third plus a fifth minus a seventh plus and so on. I want to know whether this converges or diverges. So I'm going to go through a checklist of items. Okay? Checklist of items. The first thing that I learned was all the way back in chapter 8, sequences and series. I learned about arithmetic and geometric. So I asked myself, is this arithmetic or geometric? Yes or no? Because if it's arithmetic or geometric, I know a lot about it. We know that all arithmetic series diverge. We know that geometric series only converge if the absolute value of r is less than 1. Otherwise, they diverge. So if I know it's arithmetic or geometric, easy, I'm done. I don't even have to do anything that I knew that I'm learning in chapter 20. Don't forget about arithmetic and geometric. Okay? It's the quickest, easiest way to get to an answer if it's one of those two. All right? So is this one arithmetic or geometric? Darn. All right, so what's next? Second thing, you want to test the limit theorem, theorem number 3 that we just talked about, okay? I'll call this the limit test, just for giving it a name. So the limit test. I'm going to test the limit as n approaches infinity of u sub n. So this is the limit as n approaches infinity of... Oh, I don't have the u sub n given. So I'm just going to put it on here. Okay, plus, I see that my terms are alternating, so I'm going to have a -1 to a power so that it alternates it. My first term is positive, so I'm going to do n minus 1. And then I look at the rest of the pieces. Everything has a numerator of 1. In my denominator, I have odd numbers. Well, we talked about how to easily write an odd number. 2n minus 1. Let's just double check it to make sure it works. The first one is 1 over 1. So if I plug in a 1, 2 times 1 minus 1 is 1, that works. 2 times 2 minus 1 is 3, that works. Okay? If your denominator maybe didn't have the 1 to start, it started with -1/3, then your denominator here in your u sub n could be 2n plus 1. Okay? So you can adjust that odd to make sure it starts with whatever odd you want it to start with. Okay, so there's my u sub n. So I'm going to plug that in here. So I have -1 to the n minus 1 of 1 over 2n minus 1. All right. So when I simplify this then, well, the limit as n goes to infinity of this 1 over 2n minus 1 piece, this is going to go to what? 0. So this piece here is going to go to 0. So 0 times the rest of it's going to be 0. So this is equal to 0. So I have that the limit as n goes to infinity of u sub n is equal to 0. And so now let's interpret what that means. So since this does not equal 0, does not equal 0, this tells us nothing. Those are the only tests that we know so far. Besides finding s sub n. We're not going to find the s sub n though. Okay? Besides finding s sub n, this is the only test that we have so far. So if you've exhausted all of your options, you can just say that. I've exhausted all of my options, and I have no idea. I cannot tell. I know nothing. And you're going to write that down on your paper. So this one, your sentence can be very basic as therefore can't tell. I know it's not really a sentence. Therefore can't tell. Okay? If you give an answer of can't tell, I see all the things that you tested, all the things that you tried along the way. If you forgot to test something and said can't tell, and that test would have worked, you're obviously going to get it wrong. If you forgot to test something and you say can't tell and the answer still is can't tell, and you don't show your work for something, or you tested something in your head, I'm not going to give you full credit because you haven't shown me that you've exhausted all the options. The more we cover in Chapter 20, the more options that you have. Right now, we just have arithmetic geometric and this limit test that we're going to go through. Okay? Move on. Number 2. So given 1/3 plus 4/9 minus 9/19 plus 16 over 33 plus and so on. Okay. First thing, arithmetic or geometric? So I'm thinking about arithmetic versus geometric. All right, nope. Second thing then, let's move on to the limit test. So in order to do the limit test, I need to find my u sub n. So this is going to be plus, I'm thinking about my u sub n. So I want to go ahead and find that formula. So take a moment to look for patterns. Maybe look for patterns in the numerator, look for patterns in the denominator. How can you figure out the u sub n value? Quick correction, in the middle, that should be a plus sign. So this should be 4/9 plus right here, 9 over 19. All right, so we have our u sub n, should be n squared over 2n squared plus 1. And so now we're going to find this limit. So the limit as n approaches infinity of u sub n, make sure you write that first. And then we have the limit as n approaches infinity of n squared over 2n squared plus 1. Now, wait for it. You don't have to show the divide by n squared anymore. Okay? You can use your horizontal asymptote rules. So, knowing what we know about either dividing by n squared, because that's the greatest power of the denominator, or our horizontal asymptote rules, the limit of this is going to be 1/2. All right, so that means that the limit as n approaches infinity of u sub n is equal to 1/2. Oh, 1/2 does not equal 0. Yay! Since 1/2 does not equal 0, this tells me some information. So going back to theorem number 3, you can look back on the first page at theorem number 3. If the limit of u sub n does not equal 0, then we can say that the series diverges. Very good. And we write that out in a sentence, okay? The series diverges since the limits as n approaches infinity of u sub n does not equal 0. Okay? There is your sentence for your final answer. Within that sentence, it's very inclusive of all the information that you need. It states the mathematical concepts that you're using, and it has everything to be valid that nobody can poke a hole in it. This is directly the theorem that we have, and this is why we say that this series will diverge. Okay? So in a statement like this, if you're using this, you say diverge, and you say this, and use the notation u sub n. Okay? All right, so moving into example number 3. again, we do our first check of either arithmetic or geometric. And when I look at this one, I can see my u sub n is 1 over 3 to the n. So u sub n equaling 1 over 3 to the n means that it's going to be geometric. So yes, this works. So now I need to think about my geometric series and when a geometric series will be convergent and when a geometric series will be divergent. So I know that it's geometric with the r value equal to 1/3. So the absolute value of r is less than 1, which means that it will be convergent. And then I write that all out in my sentence. So for a geometric series, we will say the series will converge since it is geometric. You're going to state the r value with r equal to 1/3. And you're going to state that the absolute value of r is less than 1. So you have converging, you have the geometric, you have the r value, and you state the stipulation on the r value that will make it converge. All right, so let's continue on with example number 4. Example number 4 here. We're given this series. We want to determine whether it converges or diverges. All right. So when I'm looking at this, I notice that every value in the numerator is a 4, and I can think about my first term as 4 over 1. And then on my denominator is just the n value. So I'm going to think about this u sub n as 4 times 1 over n. All right. So I can identify my u sub n value is going to be 4 times 1 over n. And now let's think about the different tests that we have. So the first test, is it arithmetic or geometric? And you should be thinking, no, it's not. So then my second option is I want to do the, again, like what I'm going to call the limit test. So the limit test says, let's find the limit of u sub n. So the limit as n approaches infinity of u sub n. So we're doing the limit as n approaches infinity of 4 times 1 over n. And this one can be thought of in 2 different ways. So let me just first do it by actually finding this limit since you guys know how to find the limit. So this, we know that the limit of this is going to go to 0. All right. Actually, no, it cannot be done in 2 different ways from what you know. So the limit of that, oops, we don't need that anymore. So the limit by the limit test is equal to 0. So that doesn't tell me anything. So can't tell from this. So what else do I know? Well, what else I know is I know that if I multiply a known series by a constant, then it's going to do the same thing as a known series. So number 3, is it a known series? And if you go back up to here, we had series A and we had series B. So series A here is a specific series that every single time that we have this in series A, so series A is right here. So every time we have this here for series A, this will always diverge. And so this series actually has a special name. The special name for this series is called the harmonic series. So I'm going to label this harmonic series. And that's exactly what we have in example number 4. So thinking about this harmonic series here, right? The u sub n value is 1 over n. Okay, so let's go back to number 4. So number 4, we can see that it's 4 times 1 over n. All right, so is it a known series? Yes. So it is a known, it's a known harmonic series. But then it's multiplied by 4. And that's okay because in the theorem above, I think it was theorem number 5, says that if we multiply a known series by a constant, it's going to do the same type of converging or diverging. And so Since the known harmonic series diverges, then we know that the series that's a harmonic series multiplied by a constant will also diverge. And of course, that's not just enough there. We need to write it out in a sentence. So we can say that this series is a known divergent, state what it does, a known divergent harmonic series multiplied by 4. Therefore, the series also diverges. And here, with this sentence, let me highlight the pieces that are required. You need to say it's known, you need to say it's divergent, you need to say what type of series it is, you need to say it's multiplied by a constant, and then you need to give the conclusion of divergent. All right, let's take a look at the last one, example number 5. So example number 5 here, when you look at this series, you might notice that almost all of them have a numerator of 1, except for these two terms. And if I were to take out those two terms and look at what's remaining, so 1/2, 1/4, 1/8, 1/16, 1/32, the purple stuff could just be described as 1 over 2 to the nth power, right? So it's 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth. And so 1 over 2 to the nth power, I can figure something else, something about. So 1, is it arithmetic or geometric? No. So 2, is it arithmetic or geometric? Yes. So this one is geometric with r equal to 1/2. Okay, this is just the purple. So we're just talking about the purple here. Okay, so it's geometric with r equal to 1/2. So absolute value of r is less than 1, therefore it is going to converge. But what do we do about that 3/4 and that 3/8? Well, that 3/4 and that 3/8 are two finite terms being added. So 2 terms added. And this is one of the theorems above. I think it was theorem number 1 or theorem number 4. So we added 2 finite terms. So that theorem says that if you add a finite number of terms, then it's going to do the same thing as it would do without those finite terms. So this is going to do the same thing as what the purple does by adding the 2 yellow terms. So we can write out that conclusion. So we can say that the series is a geometric series. So geometric series, and think about what we have to state about geometric series with the r value equal to 1/2, and state that absolute value of r is less than 1 with 2 added terms. Therefore, the series does exactly what the geometric series does, which is converge. Okay, so requirements here, we need to say geometric, r value, absolute value of r is less than 1, added terms, and then what it does, converging or diverging. All right, there's lesson 20.4. That is the end of today's lesson.